Well, welcome to this video about using complex numbers to create some graphical shapes, or perhaps to put it around the other way, when we're looking at some of the properties of complex numbers, and particularly the way in which complex numbers that fit certain conditions end up with either circles or ellipses or those kind of shapes. This is called loci in the complex plane. So this is just a bit of background information about common geometric graphs that you get: circles, ellipses, straight lines, and possibly hyperbolas as well. We'll have a look at. Okay, so what we're going to do, just to show you what we're trying to achieve here. So this is a section on loci in the complex plane. Okay, so the word loci, what does that mean? Well, the word loci is a mathematical term, and it essentially means a set of points that, when you graph them, fit a given condition. Or it could be conditions. Okay, so for example, if we had a point here, say point P, and the condition was we wanted to sketch all the points that were 3 centimeters from P. Well, let's say that's 3 centimeters. Well, I think you could see that if I start to sketch all the points which are 3 centimeters from P, this is just a few of them, we're going to end up with eventually a circular shape. And I'm not even going to try and attempt to draw in a freehand circle on this device here. But your imagination can fill in the rest of the points there. Okay, so what does it mean by loci in the complex plane then? Well, we'll discuss that further in class, but what we're going to see is that quite often you end up with these kind of shapes, geometric shapes. For a start, it could be a straight line, could be a circle. So given conditions, which when we investigate them further will produce a straight line or a circle or an ellipse, or haven't seen this too often, but it could happen, something called a hyperbola shape. So what we want to do here is we want to have a look at the standard equations. That was a terrible set of braces there, so where's my eraser gone? Right there. Let's try and draw that again. Okay, so the standard equations for each of these. Okay, so let's have a look at, for a start, straight lines. What we're going to find is that you can have, and this is pretty much hopefully something that you're well aware of, okay, straight vertical lines basically have equations of the form x equals a, and we'll just have a look at horizontal lines where you have y equals some sort of value. Okay, so I'm just going to swap over to the desktop here. Okay, let's minimize that, bring that back and swap to the normal cursor. Okay, let's put in a few of these equations just to reinforce that point. So x equals, say, -2. As you can see there, we've got a vertical line through x equals -2, or if we say x equals 5, vertical line through 5, y equals 3, horizontal line through y equals 3, and let's do one negative, y equals, say, -6. There we go, line down here. Okay, so that's all good, sort of reinforces that. Let's clear that screen and we'll zip back here to where we're making those notes. Okay, so getting back to the second one. Okay, a circle. Let's try and fit that in here. Okay, now a standard circle has this kind of equation form: x squared plus y squared equals a number squared, and I'm going to call it r squared because, as I'll demonstrate in a minute, we're going to find that r, not r squared, r is the radius of the circle. We'll also have a look at circles that have this sort of form: x minus a number squared plus y minus a number squared equal to r squared. And we're going to find or see in a moment that this is a circle. The radius is still going to be equal to r, but the center of the circle has moved, and the center will be at a, b. Right, so let's go and have a look at that, just demonstrate that that's true. Okay, so let's start off with, say, x squared plus y squared is equal to 9. Now remember that 9 is r squared, so this should be a circle centered at the origin with a radius of 3. Let's press enter. Yes, we can see that that is definitely the case. Okay, let's have a look at one where we're going to move the center. I'm just going to adapt this particular equation. So let's try and move it, say, 4 to the right. So that should be x minus 4 squared. Notice it's the number which makes that bracket 0, which is going to be how far across we're going to go. And let's say we're going to go up 2. So x minus 2 squared. Keep the radius the same. Okay, let's have a look at that. If we go across 4 and up 2, if I hover the cursor there, you should be able to see that there's definitely the radius is still the same, but the center point has gone to 4, 2. It's those numbers that made those brackets 0. Right, so let's adapt that again. Let's say we've got a same radius, but we want to go, say, 5 to the left and 1 down. So let's go 5 to the left. If you've been following, you shouldn't be too surprised. That'll be x plus 5. And if we want to go down 1, did I say? Let's call it x plus 1. So it should be 5 to the left and 1 down. So the center should be right where my cursor is now, and the radius 3. Alright, let's try that. Yep, seems to have worked. Cover the cursor there, saying radius 3, circle, center, -5, -1. Okay, so that's our circle essentially. Right, let's clear that. Okay, let's go back to our paper. Okay, and we'll just do one more for now, the other main key one, which is our ellipse. I think that'll do for now. Okay, a bit of room here, so let's put a summary here. So this is our ellipse. So what's an elliptical shape? Now forgive me if my hand, rough freehand drawing's not great, but basically some sort of shape roughly like that, squash sort of circle, rugby ball type shape. Okay, so either like that or that, could be on angles, but we're only going to look at ones which are sort of horizontally squashed there, or vertically sort of from the side squashed in. So that sort of orientation, or that one as well. Okay, just some sort of applications of those. The motion of a planet around a sun or star, I should say. Okay, they follow an elliptical path, and there are many other sort of real life situations where objects follow an elliptical path. So what about the equations? Well, they're very similar to a circle in a lot of ways, but we're going to find that we have some numbers where x squared and y squared are being divided. So y squared over b squared and x squared over a squared equal to 1. Now why 1? Well, that's a standard equation. I'm not going to go into all the background here, but we're going to see that this will be an ellipse, surprisingly enough. Okay, which is going to be centered basically at the origin. Man, that is a terrible ellipse. See if I can fix this up. A little better. Okay, and what about these numbers a and b? Well, we're going to see that this distance across here is going to be a, and this distance here is going to be b. And it doesn't matter if b is bigger than a, then that will simply mean you've got this sort of orientation right here. So that vertical distance up or down is larger than the horizontal distance across here. And a circle is just a special case in the ellipse where both these numbers happen to be equal to 1. Okay, and yes, we're also that number there can be different as well, but very similar to a circle in lots of other ways. Okay, and what about an ellipse where the center isn't at the origin? Like here at the moment, this is our center, 0, 0. Okay, and what we're going to find, like the circle one, if you move the center away from the origin, okay, we end up with an equation of this format. Okay, and that is exactly the same as this, except that we might have an ellipse over here, say somewhere. Where this is the center here, that this distance might still be a, negative a, b, negative b from that midpoint, but the center, okay, is now at P units across, and let me just extend that vertical axis. This distance up here to the center point is Q. Okay, so the center is at PQ. And apologies about terrible writing there. Looks so bad, I'm going to erase it and write it again. Okay, center at PQ. Okay, that'll do for now, but we'll just swap back and have a look at some graphs of this on that program Graphmatica. Just change it to that. Back to desktop and minimize that. Okay, so well, I suppose we could use this a little bit, just adapt it. So x squared plus y squared, and let's say that's over 9, and that's divided by let's say 16, and in fact we'll make this here 9, and we'll make that 16, and we'll make this equal to 1. So this, according to what I said before, should be an ellipse that has this distance across here, 4 in either direction, and should be 3 up there and down to there. Okay, let's press enter, and hopefully you can see that yes, definitely that is the case. Okay, what about moving it away from the origin? Well, let's say we want to move the origin up to, well, let's say 6 across. Well, let's say we'll go 2 down. So we want that ellipse centered at 6, -2. Alright, so we want to move across 6, and we want to go down 2. So hopefully you're getting the pattern here. X minus 6 squared, but y plus 2. So across 6 and down 2, hopefully. Yep, that seems to have worked. Hover the cursor there, you can see that's definitely an ellipse. Okay, and its center is at 6, -2. One more, just to finish off. Let's say we want to go 4 to the left and up 4. So 4 to the left should be plus 4, and 4 to the left, so that was, yep, and up 4. 4 to the left and up 4. Have I got that right? Yes, I think so. Let's have a look. Yep, cursor there, there's the center. Okay, right, that's about it. So that's our basically summary then of our 3 different ones we've looked at so far: the straight line, the circle, and our ellipse here, and the standard sorts of equations which you need to memorize. Okay, you need to know what the equation of a circle, either at the origin or at the center, looks like, and also for an ellipse. And we're going to do a little bit of work in class where sometimes we need to put them into this kind of form here. Okay, so the ones I'm talking about is this form here, this one here, this one here, and this one here. Straight lines also, but they're obviously a lot easier to recognize as long as you get the X and the Y around the right way for vertical and horizontal. Okay, that's it for now. We'll catch you guys in class.